Okay, so this first question says, using the definition of the oxidation state, not the rules that were developed, what is the oxidation state of each atom of SiS? So this is silicone and sulfur. So what we need to do here, remember that if you look in your textbook, the definition for oxidation state is the charge the atom has or would have if all of the shared electrons were given to the most electronegative atom. So let's go back here and take a look at the periodic table. Remember when we talked about electronegativity? Turn on my pen, sorry. The more we go up and to the right, the more electronegative the atom's going to be. So fluorine is our most electronegative. That's why it has that rule that it's always going to have -1, because it's always going to take the electrons. It's always going to be the most electronegative one in the group. So if we get rid of that here, if we look, here's sulfur and here's silicone. So they're right next to each other, so we can't use the higher up, the more electronegative. But sulfur is further to the right. So sulfur is going to be the most electronegative of the two. So it's going to take the electrons, and so it's going to be the one with the negative charge. And it's in this column here. Remember that the atoms that are in this column have a -2 charge, because they need to get 2 more electrons, one here, one here, to get to that ideal electron configuration state that the noble gases have. So it's going to try to take on 2 electrons. So it's going to have a -2 charge. So if we go back, so if our sulfur is -2, that's going to be its oxidation state. Remember, then that means our silicone has to be +2, because this molecule doesn't have a net charge. So these have to add up to 0. So that's going to be the oxidation state on each atom. The oxidation state on the sulfur will be -2. The oxidation state on the silicone will be +2. All right, if we look at the next one, you've just watched a video that had all the different oxidation rules on it. And you should have get a handout too that has those summarized the way they're stated in your book. Okay, so if we look at that, we're using the rules from the chapter, and we give the oxidation states for each atom in the following substance. Okay, so for this first one, we've got 3 different atoms in here. We've got hydrogen, we've got chlorine, and we've got oxygen. All right, so we have a rule about hydrogen that in a covalent compound, it's got a +1, okay, oxidation state. So I actually probably should put that as a 1+, but it's okay. We'll leave it there for now. We have a sometimes rule for chlorine, so we're going to leave that one to the last. But oxygen gets a -2, okay, in almost every situation, unless it's a peroxide, which this is not. Okay, so now if we look at this, we have -2 for each oxygen. There are 3 oxygens, so this would be a total of -6 from the oxygens for our oxidation state. And we have a +1 from that 1 hydrogen. So that gives us a total of -5, because +1 or 1 -6, okay, is -5. Which means in order for this molecule to balance out, to not have any net charges on it, this chlorine is going to have to be a +5 for its oxidation state. So what does that mean? That means in the end then for our answer, we have a -2 on our oxygen, we have a +5 on our chlorine, and we have a +1 on our hydrogen. Okay, so that's that one. All right, so when we're looking at phosphorus here, this phosphorus is just, it's the elemental compound, okay? It's got an overall charge of 0. There's nothing else. So this is just going to have a oxidation state of 0. It's just going to be 0. So that one's easy. Okay, so with the next one, we're looking at sodium and sulfur. And so when this isn't, when we have like an ionic compound, sodium would have a +1 charge. Okay, and there are 2 of those. Okay, so we have ×2. So you have an overall +2 coming from the sodium, which means it's that sulfur, which is the more electronegative, so it's going to be getting the electrons. So it's going to have a -2. So this is an ionic compound, and it's going to come together in the same way. You know, you'd have those same rules for ionic charges that you would when you were learning about the ionic compounds. And those charges are going to be what your oxidation state is in that situation where you have an ionic compound. So you're going to have +1 for the sodium, and you're going to have -2 for the sulfur. That's going to be the oxidation state of each of those atoms. Okay, so for this sulfate molecule, we're looking at the whole molecule here, and we have oxygen, remember, is one of our rules, so we'll start with that. And oxygen has a -2 charge on it. Now, there are 4 of these. All right, this should be a subscript 4, so times 4. So now we're getting -8 altogether from this oxygen. Okay, now this is not a neutral molecule. This molecule itself has a -2 charge. Remember, this is one of our polyatomic ions. So we don't want the sulfur that's in here to be balancing out to 0. So we don't want that to be an 8+, because that would make that equal 0. We want it to come out with a -2. So if this was a +6, 6 minus 8 would be -2. So that sulfur is going to have a +6 charge. And although sulfur is that more well, it's not more electronegative than oxygen, but disregard that. I don't want to confuse that. Okay, so we're going to look at that. So let's start with oxygen, because oxygen has a rule, okay, where it's -2. And so when you have that as an option, you can utilize that and start with that. And so if we get rid of all of this, then our oxidation states, then the answer would be +6 for sulfur and -2 for oxygen. Okay, so now if we look at letter E, we have calcium, we have carbon, and we have oxygen. So we have 3 different elements going on here. All right, so we have our oxygen has that 2- rule. All right, and then there's 3 of those. So this is going to be a 6- altogether. And then in an ionic compound, calcium has 2+. So we'll do that one next, because carbon can vary. Carbon can doesn't really have any rules to it. So we'll leave that one for last. Okay, so we're getting 6 negative charges from the oxygen. We're getting 2 positive charges from the calcium. And we want the net charge on this to be 0, because this is not an ion. This molecule has no net charge. So we need another 4+ to come from the carbon, so that the 4+ from the carbon and the 2+ from the calcium will balance out the 6 negatives from the oxygen. So then for your answer for oxidation numbers, you're going to have 2+ for the calcium, 4+ for carbon, and 2 minus for oxygen. Okay, so for F, we have fluorine and we have bromine. We have a hard rule that fluorine is always a -1. Okay, so even though that's coming first in that compound, and usually when we do ionic compounds, we put our negative, our anion, second. In this one, it doesn't matter. Fluorine's got that hard rule where fluorine is always a -1. So therefore, bromine has to be a +1 to balance that out because there is no net charge on that molecule. So the oxidation number for fluorine is -1. For bromine would be +1. Put the plus beforehand. Okay, get rid of that mark. All right, so the next one, we have potassium, we have nitrogen, we have oxygen. Okay, so potassium in our ionic compounds has a +1. And remember, our oxygen has a -2. Now we have 2 of those oxygens, so this is going to be a net of -4. And so this is a net of +1. So we need this to equal 4, so that will balance out. So that means that nitrogen needs to come in with a +3 in order for our positives to equal our negatives. So we'll have the potassium will have a +1, the nitrogen will have a +3, and the oxygen will have a -2. All right, the last one for H, we're going to have, we have hydrogen and we have sulfur. Okay, so our hydrogen is a +1. And there's 2 of them, so that gives us a net of +2. So that means our sulfur would have a -2, and that makes sense because that's what sulfur would normally have as an ionic compound. So the oxidative state, or oxidation number there, is +1 for hydrogen and -2 for sulfur. And that's it for those 2. I'm going to stop there. You're going to watch another video, and then we'll come back to number 3.